All right, good morning, everybody. We're going to finish up the few slides that we have remaining, and then we'll get into the day's inverted lecture. So let's look at some Lewis structure stuff that you've probably gone over in general chemistry. And we're going to look at the carbonate ion, CO3 2 minus. And so remember that Lewis structures only take into account valence electrons, so that's all we have to focus on. We know that carbon has 4, oxygen has 6. And since it's a 2 negative anion, we need 2 additional electrons. We add all that together, we get 24 valence electrons that we have to take into account. We know that our central atom is going to be which one? Why? It's the least electronegative, right? And that works most of the time, right? But we also know this experimentally. We know that the carbon is the central atom. We can observe it that way through, say, X-ray crystallography or NMR techniques, things that we'll learn more about later. And when we make the bonds to carbon, we notice that we take into account 22 of the valence electrons. And so we have to deal with those 2 additional electrons. Where are we going to put them? Why oxygen and not carbon? It's more electronegative. You always put the electrons on the more electronegative atom if possible, right? And so we do that, and now all 24 valence electrons are taken into account. But does everything have an octet as it's drawn there with the dots? What do we need to do to get an octet around everything? Okay, and why that? Yeah, but what is it that's telling us we have to have a double bond between the carbon and the oxygen? That's right, we've already taken care of all the electrons, right? But yet carbon and this oxygen at this point don't have an octet. They have a single unpaired electron, right? And they can share those in a double bond known as a pi bond, right? And we can get that structure, okay? Now, that structure is drawn horribly, right? Because why? Well, resonance is part of it, but what else? Is that really the shape of carbonate? If I have a central atom with 3 things around it, what should the shape be according to Vesper theory? Trigonal planar. And that looks more like a T to me, right? That's not a correct overall structure in terms of its accurate geometry. It's not accurate at all, okay? But the electrons are accounted for properly, okay? Now, formal charges are very, very important. You all learned in general chemistry that there's a formula for calculating formal charge, right? Forget it, because I don't know why we even teach it that way. Formal charge is a concept, and it's really easy to understand. Formal charge is nothing more than the difference between the number of electrons that an atom comes in with from the periodic table and what we formally assign to it. It's just a simple subtraction, okay? And I'm going to show you a real easy way to calculate formal charge, okay? So it's the difference between the electrons that are owned and the number that come from the neutral atom of the same element, okay? So let's look at the formal charge of hydrogen in this molecule. This is nitric acid, okay? And so the hydrogen shares 2 electrons with oxygen. Formally, we're going to assign each atom in this bonding pair, right, 1 electron. That's where we get the term formal, right? So 1 electron is assigned to hydrogen, 1 electron is assigned to oxygen. And so a neutral hydrogen atom comes in with 1 electron. It formally owns 1. The difference is 0. So it has a overall charge, formal charge of 0 in nitric acid. Now, if we look at the, what is that, Pepto-Bismol colored oxygen, right? Oxygen comes in with 6. How many does it formally own there? It formally owns 6. It owns its lone pairs. It's not sharing them with anybody, right? And it owns 1 from this bond and this bond. So it comes in with 6. It formally owns 6. So the formal charge must be 0, right? Now the green oxygen, right? Same kind of thing. It's got a double bond, so it's going to own 1 from the sigma bond. It's going to own 1 from the pi bond. And then it's going to own the 4 from the lone pairs. That's 6. Again, we get a formal charge of 0. The red oxygen, okay, how many electrons does it formally own? It owns 7. There's 3 lone pairs. It owns those completely, and then 1 from the bond. How many electrons does it come in with from the periodic table? 6. Okay, so it comes in with 6. It now owns 7. We do that subtraction. That gives us a -1 overall formal charge. Okay. Now nitrogen, right? We're looking at nitrogen. How many does nitrogen come in with from the periodic table? 5, right? So it comes in with 5, and now it formally owns how many? 4, right? There's no lone pairs, and there's 4 bonds. So it's going to own 1 from each of those bonds. We do the subtraction, and we get a +1. And so correct Lewis structure will have the formal charges shown, other than 0. So nitrogen's going to be positively charged, oxygen's going to be negatively charged. It's overall neutral, of course, because it has just as many negative charges as it has positive charges. But it's very, very important that you include all formal charges in any Lewis structure that you draw in this class. Okay? That may not have been true when you were in general chemistry, and it may not have been true when you were in high school. But you have to draw formal charges, if they exist, for your Lewis structure to be correct. The reason is because when we get to talking about reaction mechanisms, formal charges matter. It helps us explain why a reaction occurs the way that it does. Now, the easy method to determine formal charge is, can you draw a circle? If you can draw a circle, you can figure formal charge. Okay? Figure out which atom you're interested in and circle it. Everything that's inside that circle belongs to that atom. What belongs to that oxygen atom? I drew a circle. The 2 lone pairs, that's 4 electrons, right? That's right, because the circle's actually cutting through the bond, right? And so formally, 1 of those electrons will belong on the inside of the circle, 1 will belong on the outside of the circle. And so we know that we now have 2, 4, 5, 6 electrons. It comes in with 6. It formally owns 6. The difference there is 0. And you will always get that correct. You do not need to remember half the number of bonding, blah, 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 all that stuff that you learned about in general chemistry. Okay? Formal charge is a concept. How many electrons do I have in a neutral atom from the periodic table, and how many do I formally own? It's just that difference. And if you can figure that out, you don't have to memorize any kind of formula to do that. Okay? Now, you're not going to have time on some exams to sit and do formal charges all the time. You're not going to be able to calculate them all. There are some things that you just need to commit to memory. A few things that you need to commit to memory are these. There are certain atoms, if they have certain bonding motifs, are going to be positive charged, neutrally charged, and negatively charged. +1, 0, and -1. Carbon with 4 bonds is going to be 0, but carbon with 3 bonds and no lone pairs is going to be positive. If it has 3 bonds and a lone pair, it's going to be negative. You need to be able to just look at those bonds and electrons and just know what the formal charge is going to be. Okay? And you'll get that with practice. Okay? Boron with 3 bonds is 0. Boron with 4 bonds is negative. Oxygen with 2 bonds is neutral. 3 bonds, it's positively charged. 1 bond and all of its lone pairs, it is negative. Okay? So I would suggest you commit these to memory if you haven't already. It'll make your life a lot easier on an exam when you have to figure out a formal charge for whatever reason. Okay? So that finished up what we should have gotten to last time.